A computer typically has components such as a central processing unit, also called a CPU, memory, storage, such as a hard drive, I/O devices, such as a keyboard, mouse, screen, and network card. A computer uses logic gates, such as AND, OR, and XOR, to perform operations. Machine code, represented by zeros and ones, controls the logic gates. The machine code for a CPU has several instructions, represented by specific sequences of zeros and ones. The CPU executes the instructions. An operating system provides access to the computer hardware. In simple terms, an operating system is responsible for managing resources. Resources include many things, including memory, storage, and the CPU. Typically, an operating system uses a hardware abstraction layer called a HAL. The HAL allows you to plug in devices from various manufacturers and have the computer work with them. Special software, called a device driver, acts as an interface between the operating system and the hardware. A device driver makes it so that hardware from different manufacturers behaves similarly. An operating system reacts to events such as a key press or a network card receiving data. When an event occurs, the device driver for that device works with the operating system. The HAL and the device drivers make the operating system's work easier. Rather than knowing the exact type of mouse, the operating system just has a mouse that does mouse-like things. When a user runs a program, the operating system creates a process. A process contains all the information needed to execute a program, including the instructions, memory, files, etc. Each process has a time slice where the CPU executes the instructions for that process. The operating system schedules each time slice. Once the time slice for a process is expired, the operating system gives another process access to the CPU. First, the operating system gives process 1 a time slice. The CPU executes the instructions in process 1. When the time slice expires, a context switch occurs. The operating system has to save the state of the CPU so that it can be restored when the process gets its next time slice. The operating system selects the next process to run, in this case process 2, and restores its state. The CPU executes the instructions in process 2. A context switch occurs, and process 3 gets a time slice. The CPU executes the instructions in process 3. A context switch occurs, and process 4 gets a time slice. The CPU executes the instructions in process 4. A context switch occurs, and process 1 continues, executing as if it never lost access to the CPU. This is an example of round-robin scheduling. Different operating systems can use different scheduling algorithms. The computer may have more than one CPU. Each CPU can run a process at the same time as others. Now the 4 processes are executed twice as often. A CPU can also have 1 or more cores. A core is essentially the part of the CPU that executes instructions. All 4 processes can now run simultaneously. Generally speaking, the more CPUs and cores a computer has, the faster the processes will seem to run because they get more time slices. Each process gets exclusive access to the CPU, but all processes share the system's memory. The instructions and variables for each process are stored in memory. The smallest memory unit is a bit, which can hold either a 0 or a 1. Bytes are made up of bits. Computers can have different numbers of bits in a byte, but typically a byte has 8 bits. Words contain bytes. Different types of computers can have a different number of bytes per word. Common word sizes are 8, 16, 32, 64, and 128 bits. Here you can see 16, 32, and 64-bit words. Memory is broken down into lines, with each line containing 1 or more words. Different types of computers can have a different number of words per line. For most programmers, the number of words per line doesn't matter. Essentially, memory is a large array. Each location in memory has an address. An address is essentially an offset from 0, similar to an index for an array. An address can reference a byte or word, depending on the architecture. Typically, computers provide addressing to the byte level. It is easiest to think of memory as an array of bytes. A program can tell the operating system how much memory it needs. An operating system typically protects the memory of a process, meaning that one process cannot access the memory of another process. A process uses virtual addresses, allowing it to think that it has exclusive access to all of the memory. The operating system maps a virtual address to a physical address. Memory for a process is broken into segments. What segments are available depends on the platform. There are typically at least two segments, code and data. The code segment stores the instructions for the process. The data segment stores the variables for the process. Every function and variable in a process has a memory address. The data segment is typically broken into at least two areas, stack and heap. The stack stores function parameters and local variables. The heap stores variables that live longer than a function, such as global variables or dynamically allocated memory. To execute the instructions of a process, the CPU uses a fetch, decode, execute cycle. First, the CPU fetches the process's next instruction from memory. Second, the CPU decodes the instruction to determine what else is needed to run it. Finally, the CPU executes the instruction. To execute an instruction, various gates have to have their inputs changed. Remember that instructions are made up of bits, which are not easy for people to remember. Humans generally work with source code. Computers do not work with source code, so a process needs to translate from source code to machine code. A program called a compiler can convert source code into assembly language. Assembly language is essentially a more readable version of machine code. The compiler then takes the assembly language and converts it into machine code. The compiler saves the machine code to a file. The operating system takes the file and loads it into memory, creating a process that executes the instructions.